This shows the inputs and the current arrangement of pancake coils that we have designated as the 266 machine. Right now we have 0.8 volts to the left on stator phase 1, enabling 0.142 amps on that phase, and that phase is the bottom layered pancake coil. 4 winds of MegaCable, 200 feet, 14 gauge, 0.25 ohm. All 3 phases are 0.25 ohm. We're going to look at the amperages and the voltages going through these 3 phases. These 3 phases are stacked for 2 polar magnetic reactions with the middle coil polarity-wise off 1/6 of a cycle from the top and the bottom coils. This causes a cyclic effect. We will look at that cyclic effect on the scope and on the meters, but for now we're looking at the inputs. We have 0.8 volts in the unmagnetized field state, enabling 0.144 amps. We have in the middle, for some reason, we always procure a higher voltage when this load is hooked up. And we got 1.1 volts, enabling 0.243 amps. And then on the third phase again we have 0.8 volts, enabling the cyclic amperage that we'll see there. Now that's the top layered coil. Our stator line inputs are relatively balanced at 0.19, 0.24, and 0.28 amps. We could apply the law of cosines between these 3 quantities and these 3 quantities to find out if everything is adding to 360 degrees. But for now we'll let that go and on to the more important material. We see then that on the 3rd meter, we do have a cyclic amperage input. Up, down, up, down, up, down. But what we find then again, that the period when it's going up seems to be longer than the period when it's going down. And as I've noted before, this is a theory where we think that this is due to an independent phase rotation occurring. Now we'll go look at our scope. This is a scoping of that 0.8 volt signal across the top layer. And here we have an inductor on top of there. And that inductor is transforming that 0.8 volt into the top layer. We'll see our meter has gone up. It's producing 28.1 milliamps. At 185 volts. This is an astonishing efficiency. This efficiency is astonishing in light of the fact we can run a Tesla coil from this input once we actually turn the field on and procure the necessary 500 and so volts to not ignite a spark yet. But now, we've seen that phenomenal efficiency. Now we're going to look at the scope. What we're going to do now is we're going to employ the interestingly, let's see if we're getting it. More interestingly, we want to go further than that. And once again, we are seeing cyclic activity. This time that cyclic activity is being measured voltage-wise. Now here it doesn't seem, we notice that the left trace drift seems to stop when it goes down, but we don't really have a good way of seeing, comparing the time periods of when it's going up to when it's going down. And well, we're going to note that, and I think that's pretty much covered the another question here involved is on our cyclic amperage input. 97, 89, 97, 89. Well, that's probably 10%. If we've got a 10% cyclic of amperage up and down, then why is our voltage so steady state? Okay, well, I think we've run through most everything there until we can show the removal of the load. We will see that when the load is removed, try to get that in there. Hopefully we can see that meter there on phase 3 and its amperage. And when we remove the load, we should see the amperage go twice what it is now. So we're at 0.205, 208. Put the load back on there. And just for kicks, maybe we should try lighting a xenon bulb from this newly found air core principle. And if we, in fact, these 14 gauge, the 2.4 Henry load consists of 140 ohms. If we compute the I square R inputs for all three phases and compare that to the I squared R output as heat on that coil, we will find the calculations show that we have 5 times more energy going out than in, and this is all intricately related with this cyclic process that the input delivers. Okay, we want to try to light a xenon bulb with this real quick. Get in there and hook up them connections. Later on we'll show a Tesla coil being operated by this 266 configuration. Take the voltage meter off of there. Well, we'll leave it on. This voltage meter goes out all the time. We're at 184 volts. We're going to go in there and turn the field on. Now we go back and forth here and make sure that we're at 340 volts. And we can look at our scoping now, which is, seems now to be a little bit more widely fluctuating. Okay, we're going to get back here. We're going to have to go up on our voltage. We'll kind of go past 700 volts with these meters, I would suppose. Okay, we're going to take the voltage meter out of there. It's not lighted. Voltage meter out. Xenon bulb being lit at approximately 100 milliamps extraction from the secondary. We have 2 amps going into the top primary. As I can see, 2 amps on both phase 2 and phase 3, and 1.7 amps on phase 1. Our input voltages are 10.3 volts, phase 1, 15, 16 volts, phase 2, and 10.2 on phase 3, and our amperage delivery lines are 3.4, 2.4, and around in that vicinity. We'll call this one quit real quick. Focus back on that neon, and a quick scoping of that. We're now at 5 volts per division, I think, and we'll call that quits.